Right. So the last topic that I want to deliver today is some of my recent research projects, and uh, this will be a bit different from optimization we have discussed so far. But I just wanted to, I guess, explain some of my own research projects to you. So this is joint work with my students and also my colleagues at the University of Michigan Stat Department. And right, so let me talk about some, I guess, motivations for this work. So, we all know, the large language models, ChatGPT. I guess the feature that I want to say is that they use reinforcement learning with human feedback to improve their performance. Okay? And what they do is, like, even with this reinforcement learning, they receive or they generate policies using neural networks. Okay? And also, we, like, about 10 years ago, we saw innovations in gaming AI. They also model value functions and unknown value functions using neural networks. Okay. So the point that I want to make here is that, well, sorry about this. Let me. Oh no. Okay, so the point that I want to make here is that we use reward functions and or transition functions, value functions using some function class, and the applications from the previous slide were using neural networks, and there are lots of applications. So Terry games, Go robotics, autonomous driving, but so what we do is we run our reinforcement learning algorithm by approximating some, these functions using some known function classes. But they are very successful, but we lack theoretical understanding of these frameworks. Okay, so we assume some function approximation frameworks, and the goal of today's talk is we want to design algorithms for reinforcement learning with some theoretical provable guarantees. We want to argue that we design algorithms that's guaranteed to converge to an optimal policy up to certain time. I'm going to talk a bit about Markov decision processes, and that's our theoretical model. And I'll explain the linear function approximation frameworks. I guess it's quite different from complex neural networks, but I guess most of the analysis for kind of complex function classes are based on the linear function approximation. So people have assumed that your functions are approximated by linear function classes and analyzed theoretically. And the tools developed for this linear function approximation frameworks are used in more complex function classes. That's what I'm going to explain. So for the last few years, I guess the community was targeting and focusing on this linear function classes as a first step. And then recently, we also analyzed a nonlinear function class, which is given by something called the multinomial logistic function classes. That's why I'm also talk about that. But today's focus is on the linear function approximations. I will explain it. And as an extension, I will also explain the multinomial logistic function approximation. Okay, so what is a Markov decision process? So it's a continuous decision-making processes. So you at time t, you are at some state s t, and you are allowed to take some action denoted by AT. It can be a deterministic action, or you can even sample an action from a probability distribution. That's given by a stochastic policy, which I'm gonna explain in a minute. Okay, then once at state st, you take some action, then that will determine your next state. And next state is sampled from the transition function. Okay. It can be, you can kind of end up with some random state and random next state. So this pi is a policy. It's a conditional distribution. So if you at state S, you take an action, and it gives you the probability of taking this action A at a given state. Okay. But it can be deterministic in which case a single action has the old probability math and the other actions have probability 0. And at state S, let's say you take action A, and it gives you some reward. And it's coming, it's given by this reward function R. And okay, then I take action A at state S, then you get a reward R. And your next state, S prime, is determined by another probability distribution, which is denoted as this P. And we call it the probability, the transition function or the transition probability. So there are several settings. The first one is the finite horizon MDP. So like the length of the horizon is fixed, and let's say 100. So you repeat this, you make this decision-making processes for 100 time steps, and then the process is done. But you can go back to the initial state and repeat the process. You can imagine a computer game with a finite number of stages. After you complete the game, you can replay the game, but you have to start with the same initial state. That's the thing. You can also have like infinite horizon Markov decision processes. You can imagine like financial planning. It's not like you reset with the initial state. You continue the decision making processes without any stopping or without any resetting procedures. You keep continuing. The process just continues. And but depending on like how your reward is given to you, you have kind of different models. If you just put equal emphasis on your current reward and the future reward, then you set average reward setting. But if you want to put more emphasis on your current or rewards in the near future, then you apply some discounting factor, then you get a discounted reward MDP. Okay. So in reinforcement learning theory, we typically have these three different frameworks. Okay. Let me get into what they are. So first, finite horizon MDP. So we have a fixed initial state, or the initial state has a fixed distribution. Okay, so when you reset your process, you run into the same initial state, or the initial state is sampled from fixed distribution. And H is the length of finite length of the horizon. And for example, we can imagine arcade games. There are such a number of stages. When you complete all of them, you can replay the game and again and again. And so you run an episode. I'm gonna use the term episode, so that's that captures the completion of one horizon, the fixed horizon, and you can always reset your process and go back to the initial state. Okay, what about the infinite horizon average reward MDP? So again, you continue the process without resetting. Okay. So you start with the initial state as 1. Let's say time t, you are at state as t, and you take action at, and you move on to the next state as t plus 1. And you continue. You can imagine like the inventory management problem. So it's also financial planning. The point is that there's no resetting, there's no restart, but you just continue with whatever you have, and that's the problem. And the average reward is given by this expression. So let's say I have capital T time steps, and I collect this sequence of sequence of rewards from capital T time steps. And then if you divide the sum by capital T, that is the average. But if you send this T to infinity, that's called the average reward. You have a policy pi, and you collect these values. And so the optimal policy in this setting is the one maximizing the average reward. That is the thing. Discounted reward MDP is similar to the average reward setting. So the discounted reward is just that, well, you apply the discount factor of gamma. Okay. So at time t equals 1, you get R as 1 at A1. But for the next state, you apply this multiplicative factor, discount factor gamma, and you take this discount to sum, and you send t to infinity. That's your infinite horizon discounted reward. So let's say when you solve your MDP, like Markov decision process, you want to compute an optimal policy. Okay. If you are given a finite horizon MDP, you want to, depending on your problem settings, you want to compute. There's a different definition for an optimal policy. So the question is, can we find an optimal policy for your given MDP? Okay. If the reward and transition functions are known, then there are efficient algorithms that can compute an optimal policy for your given MDP. There are many known techniques. You can use like linear programming based approaches, okay, and also value iteration. You apply the value iteration multiple times, and when you converge to a certain thing, then you get an optimum policy. Also, policy iteration, it's similar, and policy gradient, which is a bit optimization based approaches. Okay. So let's talk about reinforcement learning. What is it? Well, we know that all these functions, like reward functions or the transition functions, are given to you. Then you can compute an optimal policy. But in practice, those functions are not given to you. You don't have an access to how the reward is coming from, and how the transition function is designed. So at times at state st, you take action at from your policy. Okay. But then your next state is sampled, and also the noisy evaluation of the reward is sampled to you. It doesn't have to be deterministic. That gives you one more data for you. Okay? I took some policy, and I realized that my policy is not good in the sense of getting a small, low reward. Then I can adjust my policy and update it. That is the thing. So you basically, with this data, you learn or you refine your estimation of the reward function and the transition function. Okay, and you are learning these functions. And based on that, you update your policy for the next step. And you repeat this procedure. Okay. And as you collect more and more data, you get a better understanding about these functions, and from which you can get close to the actual optimal policy. That is the idea. So I'm looking at the average reward setting, where I don't apply discounting. I add all these values for capital T time steps. This stuff that's called a cumulative reward. And I'm going to use this notion of regret to evaluate the performance of my learning algorithm. So my goal is to get close to an optimal policy. Okay. And how do I measure this procedure of getting closer to an optimal policy? Well, if you look at this expression, the first term is, let's look at the t times max, and let's look at the term inside this max expression. That's just the average reward of a policy file. Okay. If you're maximizing that expression, that is the maximum average reward. Or in other words, that's the average reward that can be achieved by an optimal policy. Okay. If you multiply that by t, that is the cumulative reward, expected cumulative reward that can be achieved by an optimal policy. The first quantity is something that can be achievable by an optimal policy, and I compared it with my cumulative reward. Okay. If this value is small, it means that my policy is doing something as good as the optimal policy. Yeah, I want to design an algorithm that minimizes this difference, which is the regret. Any question? So let me talk about some regret bounds. So for the infinite horizon average reward setting, the issue is that not all Markov decision processes are learnable. And learnable means the following. So it's hard to, for some classes or families of Markov decision processes, it's hard to guarantee a sublinear regret. And what is a sublinear? So here, the regret is sublinear if the regret grows slowly than a linear function. Okay, so that's important because if it is not sublinear, then it grows linearly. What it means is that in every time step, I make a constant error compared to the optimal policy. But when you get close, when your policy converges to the optimal policy, then this error that's made in every time step will go to 0. And if you add 0 values later, then this gap, the regret, doesn't grow linearly. So if you have a linear growth, it means that you make a constant gap, and that means that your algorithm is not converging to the optimal policy. If your algorithm converges to the optimal policy, then later on you make 0 error, and that slows down the regret. So I want to guarantee that the regret grows slowly than t, something like square root of t. So if you divide the regret by capital T, then the average regret, which is the error that you make in each time step, goes to 0. Okay. This captures whether your learning algorithm converges to an optimal policy or not. That is the okay. So we want to guarantee on sublinear regret, but but it's known that there are classes of MDPs for which deducing a sublinear regret is not possible. And the idea and the explanation is as follows. So what has to be guaranteed to design a valid learning algorithm is the following. You have to be able to recover from a bad state to a good state. What it means is, if it's not possible, when you are trapped in a bad state, and if you cannot recover from a bad state to a good state, then you remain in this bad state, and you cannot, do something good. So to be able to learn something, you have to recover from a bad state to a good state. Okay, so that's so that means that once you are if it's not possible and you are trapped in a bad state, then some bad decisions at early stages will destroy the entire learning process. So you should guarantee that you should be able to recover from a bad state to a good state. That's the requirement. And these are the classes of MDPs where recovery is possible. Even if you make some bad decisions, bad choices at the beginning, if you do something clever later on, then you will have a chance to get close to the optimal algorithm. That is what it is. So ergodic MDP is the following. If any single policy induces a single recurrent class. Okay, so you fix some policy, you run your process, and all states are recurrent. You can travel from one state to another one by a single policy. Okay, that's an easy one. And communicating MDP is a bit more complex than ergodic MDPs in the sense that you can travel from one state to another state in finite time, but it's not that all policies will do that, but you have to take some clever policy to go to another state. Okay. And weakly communicating MDP is something more general, it's not that traveling from one state to another state is possible, but there's a set of communicating classes, but the other states are transient in the sense that if you start from one of these transient states, you will go to this communicating set. So this is the generalization of communicating MDPs. And communicating MDPs are the ones, there's an equivalent characterization. You say that your MDP is communicating if it has a bounded diameter. And diameter is basically the maximum number of time steps that you need to take to travel from one state to another one. That is the diameter. Okay. And for weakly communicating MDPs, it's captured by this notion of bounded span. What is a span? The span, so perhaps this diameter is not the best way to capture the recovery from a bad state to a good state. So the span, if you look at this thing, so the V star is kind of like the value function. It measures how good your given state is. So if you look at this span, so V star is the value of your state. So this is the maximum possible value, and you measure the gap of this from the minimum possible value. So this is kind of like the value of the good state. This is the value of the bad state. So this captures the gap between a bad state and a good state. So this is the right measure to evaluate whether whether recovery from a bad state to a good state is possible. Okay. So we're gonna work on this most general class of weakly communicating MDPs where the span value is bounded. So there's a gap. There's a constant gap from between a bad state and a good state. Okay. That is what we do. And it's known that the span is always boundable by the diameter. That's done. Let me show you some regret bounds. Okay, so S is the number of states, and A is the number of actions. And the lower bound is the following. So the lower bound means that if you give me any learning algorithm, but there's a hard or difficult instances for which your any learning algorithm should incur this much regret. So this is something that you cannot hope to achieve better, hope to improve upon. Okay, so it's known that the regret is at least this value. So t, when t grows, it grows as a function of square root of t, and also the expression has a number of states and number of actions in there. And the same paper designed an algorithm that guarantees this regret bound. So it has the same square root growth. It's sublinear. Again, if you divide it by t, it's going to be 1 over square root of t. So when t goes to infinity, the value goes to 0. But there's a little bit of gap between the lower bound and the upper bound. You can use some like Thompson sampling, like posterior sampling based algorithm, which gives you a better regret upper bound. And for weakly communicating MDPs, we got this paper that gives you this regret bound. But recently, there's an algorithm that matches the lower bound, so that there's an algorithm that guarantees the best possible regret upper bound compared to the lower. So our general goal is the following. We want to prove a strong lower bound, and we want to design an algorithm whose regret upper bound is kind of as close to the lower bound as possible. That is the general goal. Is there any question? Yeah, so right. So if you have a communicating MDP, the diameter has to be always as large as the span. Yeah. But it can be that the D is plus infinity, but the span is finite. There can be a kind of large gap between them. But there's always span is always upper bounded by the diameter. Yeah, when the MDP is not communicating, D is plus infinity, but the span can be finite. But when, okay. Yeah, I mean, when D is plus infinity, this relation trivially holds. Any other question? So the theory of reinforcement learning is centering around these questions in general. You have a regret notion that captures the gap between the optimal policy and your learning algorithm, and you want to make that value as small as possible. That is the thing. So, and let's talk about the function approximation framework. Okay, let's recall the lower bound, which is given here. But the thing is that when there are a large number of states or a large number of actions, the regret bound is large. Okay. Imagine for these arcade games, there are a huge number of states and actions or states. In that case, this regret lower bound doesn't say anything. Just that, in the worst case, the regret is like huge. So we need to do something about this. But at the same time, there can be some underlying structures for a given Markov decision process. It's not, maybe this regret bound is too theoretical. And so that's why we want to approximate this reward function under transition function by some given function classes. And we can use its applications. And so my question is the following. So we assume that your reward functions and transition functions are coming from some function class. Can we guarantee a smaller regret bound? Without any assumption on these function classes, the lower bound is will depend on the number of state and the number of actions. But let's say I assume some structures, and somehow I can exploit that, and can you get a better bound? That's what's happening in practice, right? So we know an efficient learning procedure for these arcade games, for which certainly like this learning is done, and we are not like getting a large regret because we see convergence in practice. That implies that there's a nice, structures going on, and neural networks are working to, discover those unknown structures. That's what we're going to do. So as a first step toward understanding these procedures, theoretically, I guess people in the community for the last few years have started looking at these linear function approximations. Okay. So the first paper was, I think, appeared in 2017 or 19 or something, and for the last 5 years, we have seen like a big improvement and progress going on. So let me explain what it is. So linear MDP. So we assume that the transition probability is given by the product of some feature mapping. So for any pair of states and actions, we have a feature vector, and there's some state function mu s prime. So for any your transition probability is given by this. So the feature mapping is given to you. Okay. But this mu function is unknown. So the next state, still the probability is not known to you. And we are interested in the regime where this value d is small. Okay. Although the number of states and number of actions is large, but the feature mapping has a small number of values. So the task is to learn and estimate or infer this parameter function mu. And there's a related concept which is called the linear mixture MDP. That's just the transition probability is given by this expression. So I have this feature mapping for any triplet of state, action, and the next state. And there's this unknown parameter theta that is not given to you. Again, so pi is a known feature map, but this parameter vector theta is unknown. Okay. So the task is to learn this unknown parameter. Great. So let me give you the known regret bounds for like linear MDPs. Okay. So there's this paper which establishes a lower bound given by here, so d times square root of span times t. Now the regret lower bound doesn't depend on the number of actions or number of states, but it depends on the dimension of the feature mapping. Okay. So it can capture the situation where there are a huge number of states and actions, but as long as the feature mapping has a small dimension, then it can guarantee a small valued regret. The upper bound, so I guess about 3 years ago, we got this first algorithm, 4 years ago, we got this first algorithm that gives you the square root of regret, but there's a bit of gap between the lower bound and the upper bound. Okay. But this algorithm is not efficient because in each iteration you have to solve some kind of like non-convex optimization problem. So given that you can assuming you can solve this non-convex optimization, you can guarantee this regret. That is the result. Well, motivated by this inefficiency, they designed some, I guess, efficient algorithm but the regret it's much worse than the previous regret. And if you look at the dependence on t, it's going to be t to the 3/4. So it has a much larger dependence on capital T. And more recently, there's an algorithm. Well, this works for much more general settings, but it cannot be applied to the linear MDP setting. But its regret is still there's a bit of gap between the lower bound, from the lower bound. And people have looked at, the much restricted class of algorithmic MDPs, but you can guarantee some improvement in the regret, but it works for this kind of restricted class. And what we proved is the following. So we came up with the first efficient algorithm for the most general class of MDPs, but that achieves the best known regret upper bound. The previous algorithm do not really work in practice, but our algorithm is very simple and practical, but at the same time, it guarantees the best possible regret. Great, and it can achieve it implies to the case where the model 3 algorithm, but let me skip it. So it improves upon nice result, I guess 2 years ago, that appeared 2 years ago in terms of the dependence on number of states and actions. So let's move on to the linear mixture MDP case where there's a feature mapping and unknown feature vector. Still the same lower bound holds. The same paper designed an algorithm for the class of communicating MDPs, but we designed the optimal algorithm for the most general class of weakly communicating MDPs. Okay, so this is, and there's it matches the lower bound. It proves that this algorithm is optimal. So this is called minimax optima. Great. So let me explain how our algorithm works. So the first part is we have this unknown parameter function, and the question is how do we estimate and infer and learn this unknown parameter function? And we can prove that the S prime is the random next state, so its expected value, where the expectation is taken over my next state, is a linear function in the feature map. But theta star is unknown to you. So I want to learn this value. And we run, ridge regression, because this is kind of close to linear regression problem. And I have this sequence of trajectory while running my the Markov decision process, and I use ridge regression to estimate this parameter. And the another important step is this procedure of controlling the span. Okay, so I have to we have a Markov decision processes of bounded span, and controlling the span is something difficult in practice. So what we do is the following. Although we have an average reward MDP, we approximate this MDP by an average reward, a discounted reward MDP. And we run value iteration on this discounted MDP. And this is the important operation of clipping, which allows you to control the span of the intermediate MDPs. Okay, that's the thing. And somehow, it's surprising that these kind of artificial approaches work, and then it turns out that they actually work. And this is the algorithm. And this is pretty. This is a pseudocode. But if you look at this MDP, it's just that I have this parameter estimation scheme, and I have this value iteration, and I apply this clipping operation, and you just repeat. So I mean, it looks complex, but I guess just repeat these three procedures: parameter estimation and value iteration and clipping, and that's it. And the algorithm works next. And let me give you the proof a little bit. I guess the regret is decomposed as follows. So there are there are 4 different places which you incur in which you incur your regret, and there are 4 terms. So A is the error due to you are approximating your average reward MDP by a discounted reward MDP, and that's the error bound, and you can bound this. And B is this is basically like the error between your next state and your current state. It can be bounded using a telescoping sum. And the third one is something related to the martingale property, but this thing doesn't give you a martingale because there's a difference, a bit of dependencies. So the key idea is to use something called the covering argument. And the last one is due to the error because you run the optimistic argument and that thing. So we get this, we get an upper bound. But for linear mixture MDPs, we get this we get upper bound. And the key idea is we use, we are using this clipping operation, and it guarantees convergence, actually. So it's not always the case that you're applying the clipping operation leads to convergence in your value iteration. But if you apply linear mixture MDPs, this clipping operation still guarantee convergence of your value iteration. Then you run your value iteration procedure until this procedure converges, and that gives you something. And you apply ridge regression using variance reduction technique. So we run weighted ridge regression. That gives you a better parameter estimation. That's basically. So you get this regret upper bound. Okay. Let me move on to so far was the linear approximation cases. So our contribution is that linear NDPs have been studied in the community a lot, and we provided algorithms that improve upon the best possible regret upper bound. Okay, so we got the best reward. We got the best reward, best result for the case of linear MDPs. Now, but the thing is that linear MDPs, although they are kind of theoretically useful, people have studied a lot for these classes, but the linearity assumption is too restrictive. I mean, we assume that the transition probability is given by a linear function, but then it's hard to impose that's probability distribution. So the underlying model will be nonlinear. Okay, we don't have any guarantee that these functions are given by a linear function. So they propose. Recently, we got this framework given by something called a multinomial logistic function, and it gives you a nice model, nice framework to model a probability distribution. You can imagine like the softmax function, softmax activation function at the end of your neural network when you want to learn some probability distribution using a neural network. And that we have this kind of similar model here. By definition, it gives you a probability distribution. And you assume here that pi is a known feature mapping, but theta is an unknown parameter. So we are still interested in the case when the dimension of the feature mapping is bounded. Okay. So there are some regret bounds. So for finite horizon, the upper bound is given here. So K is the number of episodes. So K, we run this process and reset, and we count the number of episodes we run, and the regret upper bound is given here. And what we proved is that the lower bound is close to the upper bound. Okay, there's a gap in terms of the number of time steps for an episode. And for infinite horizon setting, we designed an algorithm that guarantees this regret upper bound. We also proved that the lower bound is given by this expression. There's a little bit of gap in terms of the span parameter. So we got these results. And to prove the lower bound for the finite horizon case, we have to construct this class of Markov decision process. And if you do, we can prove that for any algorithm, you need to incur this much regret that using this instance. And also, we provided this algorithm. And when you analyze or learn the parameter, unknown parameter, we have to use the maximum likelihood estimation using this log likelihood function. And when you run the recent technique of online Newton method to learn this model. And for the lower bound, we are incurring this instance, and that gives you this much regret value. Okay. So I guess this is pretty much it. Thank you.